Okay, so welcome to part 3 of this video, in which we are discussing the reason that the L-infinity space is complete, basically. Okay, so we've said that to prove that it's complete, what we need to prove is that this sequence here, this sequence of sequences, converges to this sequence L. And what we've said so far is that this sequence here of sequences is Cauchy with respect to the d-infinity metric. And from that we gained the fact that each of these term-wise sequences, so where you take a specific term from each of these sequences, and that's a sequence of real or complex numbers. Basically, the sequence being Cauchy with respect to d-infinity implies that these are all Cauchy sequences within the real or complex numbers, and therefore they are convergent. So this being Cauchy implies that it is pointwise convergent, that this sequence of sequences is pointwise convergent, and it converges pointwise to this sequence down here. And now in the previous videos we've shown that if a sequence is convergent with respect to d-infinity, then it's also pointwise convergent, and in fact the limit of the sequence in d-infinity is exactly the pointwise limit. Okay, so if it does converge with respect to d-infinity, we've said it's absolutely going to converge to this. It can't converge to anything else. All we have to now prove is that it actually does converge to this, because there is a possibility, of course, that it doesn't converge to anything at all. Okay, so to prove that it converges to that, what we need to prove is that I can find you some big N, such that if I take any sequence S little n that's beyond big N, and I pick any one of the terms of that sequence, and I take its difference between Li, then that's going to be less than epsilon. So this supremum being less than epsilon means basically that any term is less than epsilon. So if this is true for all I is an element of the natural numbers, and for all little n is greater than or equal to big N, then it will be true that this supremum is less than epsilon. So if it's true for all little n, then you fix the little n, and then if it's true for all I is an element of the natural numbers, then this set that you form here of all the terms, so when if we fix our little n, then it's just something greater than or equal to big N, then what we do is we build the set. So we build the set which contains the modulus of x little n 1 minus L1, and then we add in x little n 2 minus L2. So we take every single the difference between each of these terms, take its modulus, stick that into a set, and we do this for absolutely every single term. Take the supremum of that set, and we want that to be less than epsilon. Well, that will be less than epsilon if all the terms in this are less than epsilon. And basically, it's got to be true, that's got to work for all little n is greater than or equal to big N. So that will be true. It'll be true that this is less than epsilon for all little n is greater than or equal to big N if every term of this set is less than epsilon, and it's true. So this is if for a fixed little n, and now we're saying, okay, it's got to be true for all little n greater than or equal to big N. So hopefully that convinced you that if we want this supremum here to be less than epsilon for all little n is greater than or equal to big N, it implies that for all I is an element of the natural numbers, and for all little n is greater than or equal to big N, this has to be true here. Okay, so how are we going to prove that? Well, we're going to use the Cauchy criterion, the fact that these sequences is Cauchy sequence with respect to d-infinity. So it being Cauchy means that for all let's say delta greater than 0, so whatever delta you give me greater than 0, there exists some, I'll call it big H, which is an element of the natural number, oh dear, what have I done? The element of the natural numbers, such that if little h and little g are greater than or equal to big H, then the distance between s little h and s little g has to be less than delta. So basically what that means is if I draw the sequence out, s is equal to the sequence s1, s2, etc., then there has to exist some point s big H such that if I go beyond that point and take any 2 points in the tail end of this sequence, so s little h and s little g, then the distance between them with respect to this infinity metric has to be less than whatever delta I pick. Okay, right, so we'll now expand that further, so we'll substitute in what d infinity was equal to. So this sequence s little h was equal to some, this was a sequence, remember, of real or complex numbers, so let's write it out. It's xh1, xh2, xh3, etc. And the sequence sg was again another sequence like this, so xg1, xg2, xg3, etc. And the distance between sh and sg here is going to be, by definition, because it's the infinity metric here, is the supremum of over I is an element of the natural numbers of the modulus of xhi minus xgi. So what you do is you go through every single term, you take the ith term in the sh sequence, you take the ith term in the sg sequence, you subtract them from one another, take the modulus of that, and you put them all into a set for every single I is an element of the natural numbers, and you take the supremum of that set. So that's the distance. So basically what we're saying is, if I draw this picture out again, so we've got S1, S2, S3 here, and these are the sequences x11, x12, x13, and I apologise for how much of drawing this picture out again I have to do, but it really is very important for intuition over this. x22, x23, etc. So these are the sequences in this sequence S. So x31, x32, x33. Okay, and then what I've said is we have some S big H over here, which is x big H1, x big H2, x big H3, where if you go beyond this point here and you take any two sequences beyond that, s little h and s little g, which are these sequences, I'll put them in, x8 little h1, x little h2, x little h3, etc. And we've got this sg, which is x little g1, x little g2, x little g3. Okay, so if you go beyond this s big H and pick any two sequences, then the distance between them has to be less than delta. So whatever delta you give me, I can find you in big H for which this is true. So sh, sg has to be less than delta, and that implies that just substituting this thing up here in, that the supremum over I is an element of the natural numbers of this modulus of x little hi minus x little gi has to be less than delta. Now this is a great big set, so remember this is the supremum of the set xhi minus xgi, where I is an element of the natural numbers. So if this supremum is less than delta, it implies that all the terms in here are less than delta. So x little hi minus x little gi has to be less than delta for all of those terms. So for all I is an element of the natural numbers. But this also works for whatever little h and whatever little g you pick that are greater than or equal to big H, basically. Right, so here's the thing. We were trying, remember what we were trying to do? We were trying to find some big N such that if you go beyond it, all of these terms, if you take an arbitrary term, well, firstly you pick an arbitrary sequence Sn, and you pick an arbitrary, you pick the ith term of that, then that's distant, that the modulus of that term, take away its corresponding term in this limiting sequence over here, so Li needs to be less than epsilon. Let's let delta equal epsilon over 2, basically. So we've said let epsilon be some arbitrary number greater than 0, and I'm trying to find a big N for which this is true, basically. So I'm saying, okay, let this delta that we're working with in the Cauchy criterion, let it be equal to epsilon over 2. So I can find you a big H, so there exists this big H, which a big H, which is an element of the natural numbers, such that if little h and little g are greater than or equal to big H, that this criterion here is true, because once we broke down all of this metric stuff, this is what it overall came down to, that the modulus of xhi minus xgi is less than delta, but delta is now epsilon over 2 for all little h and little g is greater than or equal to big H, and for all I is an element of the natural numbers. Okay, so that is close now. What this is saying basically is if you take any term x little hi, such that it is below this line here, i.e. that it's from a sequence which is further along than the sequence S big H, then if you take that term and you take another term from any other sequence that's beyond SH, and it's the same corresponding term, so you have to pick the same term, you have to pick the same ith term in this case, then the distance between them is going to be less than epsilon over 2. Okay? But what we wanted to show, remember, was we wanted to show that for all n is greater than or equal to some number, and for all I is an element of the natural numbers, I can make this less than epsilon. But, so, let's take xhi. Basically, what I'm going to do is I'm going to say let big N equal h now. Let big N equal h. And I want to show you that if I pick any point in here, so xhi, so I pick the sequence sh, i.e. a sequence that's beyond big H, so that's just any sequence that's further along in this meta sequence here than the S big H sequence, and I take any term from it, so I take the ith term, then I want to prove that that the distance between that and the corresponding term in the limiting sequence, which I haven't drawn, so I'll put this down here, L is equal to L1, L2, L3, which is the sequence we're trying to prove that this sequence of sequences converges to, so I'll put Li down there. Okay, the distance between that, I need to show you that that is less than epsilon, so this is what we need to show. So, oh dear, sorry, to show this. Okay, right, well now I just use the triangle inequality in the real or complex numbers to say that xhi minus li is strictly less, well, sorry, is less than or equal to the, so this is the distance between a point xhi and li. So the distance between this point here and this corresponding term here is going to be less than or equal to xhi minus some xgi, where xgi is some arbitrary term. It can be any, g can be any number as long as it's greater than or equal to big H. So it's any, it's one of these, it's in this column basically, but we don't know what height it's at. All we know is it's beyond big H, okay? So minus xgi plus the distance from xgi to li. So basically, this here is the distance between these two here. So that distance there. This one here is the distance from this to this, and this one here is this distance from here. So that's just the triangle inequality, basically. Okay, right. Now, I'm saying that if I picked big N to be equal to H, so this thing here is guaranteed to be less than epsilon over 2, basically, because I chose big H such that if you went for all sequences beyond big H, all of the terms of that sequence, if you chose any one of these sequences, SH, and you chose the ith term, and then you chose any other sequence, SG, and you chose the ith term of there, then the distance between them has to be less than epsilon over 2. So I chose big H so that that was going to be true. And so we used the Cauchy criterion on this sequence of sequences to do that. So we know that this is less than epsilon over 2. So all we need to prove now is that I can make, I can choose the xgi, I can choose my g. The g is free, remember. G can be any number that's bigger than big H, basically. Any natural number that's bigger than big H. It's any one of these terms in this sequence, basically. So I want to prove that I can make this also less than epsilon over 2. And the reason I can do that is because of pointwise convergence. So because of pointwise convergence, this sequence of the ith terms converges to Li. What's the meaning of that? So here's Li here, and the sequence of all the ith terms, so the ith term from sequence 1, the ith term from sequence 2, the ith term from sequence 3, etc., it converged to Li. Remember, that was how we came up with this sequence L, that it was the limit of the sequence of ith terms. So, if you give me any interval around Li, I can find you a point in this sequence of ith terms, such that if that term and beyond are all contained in here. So basically, if I let this interval be Li minus epsilon over 2 to Li plus epsilon over 2, so I'm making the interval of radius epsilon over 2, then there exists some, what should I call it, some m, there exists an m, which is a big M, which is an element of the natural numbers, such that if little m, let's say, is greater than or equal to big M, it implies that the modulus of the xmi minus li, so that's just the distance of the nth term of this term-wise sequence. So remember, I is fixed because we've fixed the term of this, the terms of this sequence of sequences that we're looking at. So I is fixed. We're now varying what sequence we take it from. So this is the nth term of this sequence. So it was taken from the nth sequence over here. So what? Basically, if I make, there will exist some big M, which I'll put here, some x big M I, such that if you are beyond that term, if little m is greater than or equal to that big term, that big M, then the distance of this term x little m I to the limit Li will be less than epsilon over 2, i.e. it will be contained, if you go anywhere beyond this term in the sequence, you will still be contained within this epsilon over 2 interval. And because this converges to there, that's just the definition of convergence, that I can do that. Okay, so basically you just have to find a term, the way you pick xgi is you make sure that xgi is beyond x big Mi. So the way you're going to choose g is you want firstly g to be greater than or equal to h. So you want it to be beyond this h, otherwise you don't have the Cauchy criterion. So you can't guarantee that xhi minus xgi is less than epsilon over 2 unless the g is greater than or equal to h. So the term has to be beyond this point here, but it also has to be beyond big M. Now big M might be, you might be lucky, big M might be prior to big H. So if it's bigger than H, you might automatically get that it's bigger than M. But big M could actually be on the other side of H. So this is H here, and if it is, then you're going to have to go further. So you want G to be bigger than big H, but you also want G to be bigger than big M. So if it's got both of these, if both of these are true, and you can always find a G such that both of these are true, because both of these numbers are finite natural numbers. So just take the maximum of them. If you make G bigger than that maximum, then you're in business. So let's say, for argument's sake, that M is beyond big H. So big H is smaller than big M. Then you're going to have to pick xgi below that M. And if you do that, though, then first you're guaranteed that this is less than epsilon over 2 because G was beyond H, so it had the Cauchy criterion working in its favour, and you're also guaranteed the fact that the difference between xgi and the limit Li, the pointwise limit Li, is also going to be less than epsilon over 2, because I said, okay, make this interval around Li epsilon over 2, so that if G is beyond big M, it guarantees you that it's within that interval, which implies that the difference between it and the pointwise limit is less than epsilon over 2. Okay, so we add those two things together now. Yep, we need a new sheet of paper. It seems a bit wasteful to start a new sheet of paper when we're so close to the end now, but I'll use it again in another video. Okay, right. So, if we add these two things together then now, what we get is that the modulus of xhi minus xgi plus the modulus of xgi minus li is going to be less than epsilon over 2. So what we have basically is that xhi minus xgi must be less than epsilon, sorry, no, not that. We have basically that this thing here, the distance between xhi minus li must be less than epsilon, okay? So, and that works for all I is an element of the natural numbers, and for all H is greater than or equal to big H. So basically, what we did, and let me just say it in words, what we did, we said, use the Cauchy criterion. The Cauchy criterion tells us that if I want to make all of these corresponding terms closer than epsilon over 2, I can do that. So do that. Find this sequence beyond which, if you take any two sequences, s little h and s little g, and compare corresponding terms in those sequences, then the distance between the corresponding terms is going to be less than epsilon over 2. We also know that because all of these term-wise sequences converge to this point-wise limit here, then at some point there will be a point where all of the terms are closer than epsilon over 2 to this. But if these terms here are closer than epsilon over 2 to this, and all of the terms in here are closer to one another by epsilon, that implies that any term beyond this big H is also going to be within epsilon of this limit basically over here. That's what we've done. We've combined the two things together basically to get overall that if you go beyond this S big H and you take any term, and you want to know what's its distance, so you compare it to its corresponding term in this limiting sequence here. So if you've got the ith term of, you take the ith term of whatever sequence you've picked, and you're comparing it to the ith term of this limiting sequence here, then the distance between them is assured to be less than epsilon, because what I can do is I can say, okay, the distance between this term and any of the other terms in any of the other sequences basically, so any other term in any other sequence that is ith, so all the other ith terms in all the other sequences that are beyond S big H are going to be within epsilon over 2 of me. But I can find you a term basically that is then going to be within epsilon over 2 of this limit basically, because the sequence of ith terms converges pointwise to the ith term of this limiting sequence here. Okay, so that's what we've done basically. So we have shown that if you take big H, if you take a point from the SH sequence such that little h is greater than or equal to big H, you can do whichever term you like. Any term which is an element of the natural numbers, it's going to be within epsilon of its pointwise limit. Okay, and that's exactly what we needed to show that that the distance between any sequence SH and the sequence and the limiting sequence is less than epsilon, because this fact here implies that the supremum over I is an element of the natural numbers of this modulus of xi hi minus li is less than. Well, actually, it would strictly imply that it was less than or equal to epsilon. But of course, we could then just we could just make epsilon arbitrarily bigger than that. So it wouldn't matter basically that. Strictly speaking, if you've got a bunch of things in a set and then which are all strictly less than epsilon, and you take their supremum, it could be less than or equal to epsilon. But then just add an arbitrary tiny, well, when you are given your original epsilon, just subtract some arbitrarily tiny number from it and then do it for that, and then it will be less than that arbitrarily. So basically it will work that the supremum of this set is less than epsilon, and that works for all h is greater than or equal to big H, which implies exactly this, that for all h is greater than or equal to big H, the distance of that sequence from the limiting sequence L is going to be less than epsilon. So that basically proves that any Cauchy sequence in the L infinity space is going to converge to another sequence in the L infinity space, and therefore that the L infinity space is a complete metric space.